So vectors are essentially straight lines of motion, and the idea of a vector is we have direction and magnitude involved in both of them. So we both have a direction and we have a magnitude, which kind of is which forms the idea of a vector. So we've been working in the universal scalars before, which just had a direction, just had a magnitude, but no direction. So essentially it was just this component before, rather than the full, it was just like, oh, it's a magnitude of 3, magnitude, we've just been working with like stuff on the number line. Now what we're doing is essentially we're saying that this has a certain direction as well. And what can give it direction is the things that we just started talking about in terms of the angles and what we can do. So this is another way. This is often used more for complex numbers, but you can kind of see how it can be represented that way as well. So a couple ways to represent it and a couple things about it that are important. So you can represent it in this form, which is essentially the broken down form into the individual components. So the I component shows how much horizontally it's moved, and the J component shows how much vertically it's moved. Another way to represent it is using column vectors, so that using our column matrices. And if we look at those, another way also to represent it is you can also talk about it being between 2 points. So if we talk about the vector from A to vector B, essentially what you can say is that it's just the 2 points minus from each other. So that's another way you can talk about it as well. The couple things about it, so when we're kind of using the magnitude, so we're finding the magnitude of the vector, what we can do is just using that a squared plus b squared thing for a similar reason to why it worked in polar form. If we look back to here, if we imagine like a line passing up through here, you can kind of think that's going to be the same line that's passing through there, and then you can kind of figure out the coordinates from there and draw a triangle to figure out exactly how long that line is. Cool. So in terms of adding or minusing vectors, it's like you can do it a couple different ways. So it's pretty visual in terms of how it works. So you can, a way that they talk about it is like the head to tail type thing. So what you can do is you essentially just go head to tail, and then from there it helps you make sure that you're staying in the right direction. So you can essentially just go head to tail. So what the head part is this part here, and the tail part's here. So essentially as long as they connect, that's the correct way to add together vectors. So you're going from head to tail, head to tail. And so you can kind of see how this is a plus b, whereas this is a minus b, and all you have to do to go from negative to positive is just flip the direction of the vector, because now it's going in the opposite direction. If you want to add just without the visual component to it as well, an easy way to do it is if you have it in the form of like going from this point to this point. So for example, AB plus AC or something like that, right? So what you want, how I like to think of it is like, this is like my algebra way of the head to tail. So what you can do is you just like switch the letters. So as long as the letters connect, it works out. So essentially you can have BA plus AC, or negative BA plus BAC, more like, because there's the negative component as well. But if you kind of switch that around, essentially what you're going to get is that you can see how there's AC component would kind of connect together, or if you wanted to add those two vectors together, right, you would have to like move this vector up there. So an alternative way to get BC would just be, rather than, you're going to use those two vectors, but you're just going to switch around this direction. You're going to just switch around the direction of this one. So if you wrote this out, this would be BA plus AC, so you can kind of see how the letters connect there. And then if we wanted, in terms of those two vectors, it would just be negative AB plus AC. It would be negative, if we wanted the two vectors, so if we wanted BC, we would just say that it's going to be BA plus AC, so you can kind of see how those two letters connect together nicely like that. So therefore you're going to have negative AB plus AC. Cool. Alright, so then another thing with our vectors is this special dot product type thing. So this is essentially called the vector product. the scalar product, and there's also another thing called the vector product or the cross product, right? And that's something you're going to learn next year, and it's a new part of the study design, used to not be part of the study design, but essentially it's talking about like a vector which is perpendicular to both vectors. For this year, all you have to know about is the dot product, and the dot product is really, really helpful for what you need to do. So it's a special operation for vectors, and it's when there's no geometric representation of the dot product. So the vector times a vector gives you a number. So essentially it's those two times together. So another formula that you can use for it is this one, and why it's really handy to have both formulas is just like when we were doing for our cosine and sine rules and all that kind of stuff. What this actually allows you to do is it means that you're going to be able to find out what the angle is as well, because you have two rules, and if you can kind of times them two together, you could get the two rules. Or if you have the angle and they have the magnitudes, that's also another way to find it. Another important thing that is involved in the unit of vectors is that idea of a vector projection. So what a vector projection essentially is that it moves in the direction of u, and the unit vector is essentially a vector which has the direction of whatever vector it came from, but it has no or a very innocuous magnitude, which is just one, right? Because it's one unit. So essentially it's used in the idea that still has the direction of what it originally needed to have, but now it no longer has the magnitude of it, so it can be used in a really helpful context. And the most helpful context it's used in is something called vector projections. And essentially what a vector projection is it shows you how far one vector is moving in the direction of another vector. So you can get a perpendicular by finding, minusing the a parallel from the a perpendicular. Because if you imagine that, so that's the a vector, and then if you minus it from there, you can kind of imagine the head to tail situation. So how you find a parallel is essentially what you're saying is that how far is my vector A moving in the direction of vector B? So what that means is essentially you want to find out how far it's traveling, and then you want to put it in the direction of vector B. So an easy way to write it is essentially A dot vector B dot vector dot unit vector B again, because essentially what it is how far is it moving in the direction of B, and because this is a unit vector, it won't affect the magnitude of it. And then you're going to times it by unit vector B again, because you're going to say, okay, this is the actual direction of B, so I'm going to move it in the direction of B, and that gives you a vector of how much A is moving in the direction of B, so how much it's projecting in that direction. So there's a lot of different ways to write it and figure it out, and you can use any formula you like, as long as you're comfortable with it and happy with it. But the main thing is that you need to make sure that you choose one and then just kind of commit to it, because the formulas can get a little bit long to do sometimes. Cool. Alright, so we'll have A parallel will equal to A parallel times vector B, A dot B over this. So that's another way to write it as well. So you can see that there's like hundreds of ways to basically use it, so it's kind of up to you what you want to do. And remember, the unit vector of B is just going to be vector B over the magnitude of the B vector. Cool. So if we want to find a triangle which has the vertices of like A is root 3 plus 1, and then negative 2, 4, and then we have the other vertice which is 1, negative 2, 3, and C which is 2, negative 2, root 3 plus 3, and you want us to find the area of this triangle. Essentially what you can do is we can use this area equation that we found before, so that area equation that we've used, and what we want to do is we'll get a half AB BC times root 1 minus cos angle of cos squared. And why we want to use this angle is because it'll be the easiest one for us to find in terms of the actual angle component of it. So we can find what AB is. So AB is going to essentially just be AO plus OB, AO plus OB, so it's going to be the negative of whatever this is plus this part. So it's going to be 1 minus root 3 plus 1, then it's going to be negative 2 minus negative 2, then it's going to be 3 minus our 4, right? So we're going to end up with root 3 plus 0, j minus k. And then similarly for the BC component, we're going to have this is going to be BO plus OC. So it's going to be BO, which is negative 1 plus 2. So that's going to be 1. Then we're going to get negative 2 negated, which is 2. So 2 plus negative 2 is 0. And then we're going to get negative 3 plus root plus negative 3 plus 3 root 3 negative 3 plus 3 plus root 3, which the negative 3 and the 3 are going to cancel out, and you're going to just get left with root 3. So then what you're going to get here is we've already found out what these two components are, and now the next part we need to find out what our cos value is. So our cos value is going to be our AB times BC over root AB BC. So we can times that in, and what we want is if we times those two, so we're going to times these two and then divide by the magnitudes of each of them. So what that means is in this process we will need to find the magnitudes and do that as well, so we can kind of do that in our process now. And so what we're going to say is we could say magnitude of AB is going to equal to negative root 3 squared plus 0 squared plus negative 1 squared. So that's going to be root of 3 plus 1, so i.e. 2. And it's going to be the same for this one. And then if we multiply across, what we're going to get here is that it's going to just be negative root 3 minus root 3. And what that's going to give us is negative 2 root 3 at the top. So if we kind of move to the next slide, we can kind of see how that was introduced. So our negative 2 over root 3, now 2 times 2, which is going to just give us negative root 3 on 2 as our angle. So what we can do is we can plug that in, and we'll get that this is negative root 3 plugged in there. So we'll get that the angle is going to just be 1 plus, essentially, 1 minus 3 on 4, which is going to be 1/4. So it's going to be a half in there. So we'll essentially have a half times 2 times 2 times a half, which will just give you an area overall of 1. Alright, so let's talk about doing a vector resolute now as well, and how we can find our vector resolute equations. So they want us to find the vector resolute between A and B, and if the magnitude of B is 3 units and the angle between A and B is pi and 3, they want us to find the vector resolute of B in the direction of A. So what we can do here is essentially we can just put in that, so that we can talk about the different formulas that we can use here. So we can use A dot unit vector B dot unit vector B, right? So that's one way to do it. Or alternatively, you can do A dot B over B dot B. So that's another way you can also represent that same vector, or a parallel vector. And then you can also do, some people also like to do is equivalent to A dot B over unit vector B squared dot B, like that. So there's a couple of different ways to do it, and it's up to you which way you want to do it, essentially. Either or is fine, whichever thing you're most comfortable with. Alright, so let's write. Well, I like the one where you do the unit vector B part, so I'm going to go unit vector. Actually, I like this one, so I like to go like A parallel will equal to A dot B over B modular squared dot B. I like to do that one because I think it's the easiest. So if the magnitude of B is 3, so B equals to 3, and the angle between A and B is pi and 3, so if we're looking at this part, so A dot B will equal to unit vector A, unit vector B, or not unit vector, sorry, modules A, modules B, cos pi on 3. and we want to find the vector resolute of A in the direction of B, right? So we can put that in so that we want to find what A, therefore the unit vector of A is going to be. Sorry, the unit vector, the modulus of A. So that's going to be 4 squared plus 5 squared, which is going to just equal to 16 plus 25, which is going to equal to root 41. So essentially, A dot B is going to equal to root 41 times 3 times cos pi 3, which is going to be a half. Okay, so that's going to be 3 root 41 over 2. So if we kind of plug that back into the process there, we'll get that this is going to be 3 root 41 over 2 over b squared, which is going to be 9, and then times our b vector. So all in all, what we're going to get here is A parallel is going to be equivalent to our 3 root 41 over 18 times our b vector, which is going to be bi and then ji. Vector resolute plus bi plus bj. Okay, so that means that we actually need to find what the vector b is as well, right? So we've gotten some information about exactly what's going on in terms of like the a and b, right? And they've told us that the angle, the value of between a and b is going to be exactly that. So if we can do this as well, we'll get that this will be 4b plus 5b essentially will equal to our vector a, vector b, cos theta. That's another way that we can represent it, right? And we know what a is, we know what b is, we just found that. So we know that this is going to be 3 root 41 over 2 is going to be essentially 9b. So b is going to equal to 3 root 41 on 18, which coincidentally is actually the same value here as well. So that's kind of a bit funny. But essentially what we're going to get here is we can substitute now that back in. So we'll get A parallel will equal to 3 root 41 on 18, essentially times 3 root 41 on 18 times I plus j. So if we could substitute that in now, what we'll get is going to be, it's going to be root 41 squared. So it'll be 41 times 9 on 18 times 18, which is just going to give us 41 on 36. And then we're going to have I plus j. Cool. So another, oh, I keep on doing that. I'm so sorry, guys. I'll just rewrite that bit. Root 41. Let's rewrite that bit. So we'll get that A parallel will equal to root 43 root 41 times 3 root 41, which we worked out to be 41 on 36. And then we can put that into that bit as well. So we'll get that this is going to be just I plus j. Now, sometimes in other questions as well, they also ask you for like the perpendicular component, because it's another thing that they can do as well. So they ask you for like, oh, what's the perpendicular component, or what's the shortest distance possible, etc. So if they do ask you for that, another thing you can do is you can, let's white out what's on this page. So we know that A parallel was equal to 41 on 36 of I plus j. So sometimes they ask you for like the shortest distance which is a bit ambiguous, but essentially what it means is it wants the magnitude of a perpendicular to b. Sorry, perpendicular to b. So what that means for us is all we have to do here is just go a minus a perpendicular to b, and what that's going to give us here is it's going to give us 4 minus 41 over 36 I plus 5 minus 41 over 36 j. So what we're going to get here is that if we times that by 36, there'll be 144. So 144 minus 41 over 36i, and then plus 180 minus 41 over 36j. So what we're going to get here is it's just going to be 103 on 36i plus, you'll often get really awkward numbers for this just because of the way that it's found, 139 on 36j. And then they want the magnitude of it, so we can just say the shortest distance a perpendicular to b is going to be equivalent to root of 1 on 3 over 36 squared plus 139 over 36 squared, which if we work that out on our calculators, 103 squared plus 139 squared over 36 squared rooted will give us that it'll be root 29,930 over 36. So that will be the shortest distance between A and B. Cool. Last couple of bits are talking about your vector proofs, and what's most important for your vector proofing is that you have a good system of the geometry properties already. So that's really important and like kind of vital, I guess, to this. So it's vital that you have a good understanding of all the geometry properties involved in just basically everything. So what I would recommend is like a table or like a sheet with all the geometry stuff. So stuff that comes up really commonly, like I mentioned before, is like circles and parallelograms. They really love them in proofing and vectors for some reason. You'll see them in 3-4 VCAR exams. You'll see them basically spread out essentially everywhere. So it's really important that you can get them down early and easily, and that way you just have all the rules on hand and become comfortable with using them. They also like triangles a lot as well here, so it's important that you know all your geometric rules for triangles, so know your basic rules and your kind of more advanced rules as well, so the rules that we just talked about in terms of that sine cos type thing. Cool. Alright, so let's do that there. So we'll draw out our diagonals. So they want the diagonals of a parallelogram to bisect each other. So what we know about a parallelogram is, in the simplest manner, we know that it's parallel in terms of the opposite sides. So it goes up here and it goes up here, it goes here and it goes here, right? So we know that those components that's the kind of essential components of it. We also know that for a parallelogram, opposite sides are equal and parallel. And that's our main thing, right? So what we can do here is essentially just label our sides with like letters. So we can say this is A, B, C, D. And that way we can kind of talk about the thing. So we know that AD will be equal to BC and AB will be equal to DC. So that's our ideas. And then they want us to prove that the diagonals bisect each other. So essentially we can kind of draw a line from A to C, and then we can draw a line from B to D, and we want to prove that this point X, right, is going to bisect that line there. So what we can do is, because they bisect each other, we can just say that we can assume that there is along AC this point X which sits there already, and we'll bisect that. And our goal is to try and prove that that point also bisects that line BD. So what we're going to get here is that we're going to get that firstly, AC is going to be equivalent to our, let's say, BA plus our AD, right? Oh, sorry, AC. Let's rub that out. So our AC is going to be equivalent to our AB plus our BC. So that's where our line is going to be. And therefore, we're saying let X be midpoint let X be midpoint of AC, right? So what we're going to get here is AC is going to equal to a half AB plus BC. And that's going to be our line already, right? So then what we can do here is now we've found what AX is. And we can kind of leave that as is. Now what we want to find is what BD is. So BD is going to be equivalent to our BA plus our AD. Now we want to make these all equivalent to each other, right? So that it's just easier for us to do. So rather than saying AD here, we can replace that with BC because AD was equivalent to BC. So essentially it's going to be negative AB plus BC, right? In order to get this diagonal here. So then what we can do here is essentially we can just put that in because now we have this value that we can just work with that we don't need to worry about. Now we have everything in terms of the thing, so we don't really need to worry about all of this type of stuff anymore. So now what we need to find is we need to find what BX is going to be. So BX is going to be BD plus DA, right? Oh, sorry, BX plus AX. What am I talking about? Let me just rub that out. So it's going to be BD. Well, let's go BA. So it's going to be BA plus our AX that we found before in order to find it, right? So you can see how the A's connect there. So therefore our BA is going to be we can get that from essentially this part here. So BA is going to just be negative AB plus our AX, which is going to be minus plus 1/2 AB plus BC. So we can say that's going to be now negative 1/2 AB plus 1/2 BC. And I will stop writing there so that I can. So our BX will be negative 1/2 AB plus 1/2 BC, which we can kind of see is going to be just negative 1/2 of negative AB plus BC. So essentially it's just going to be 1/2 of our BD. So therefore X is also midpoint of BD. So therefore we can kind of say that the diagonals of the parallelogram bisect each other because essentially the midpoint of that one was the midpoint of that one as well. Coolios. Alright, so this last question here is about triangles. So Prove that the altitude of a triangle is the perpendicular bisector to the opposite side. So if the altitude of the triangle is the perpendicular bisector of the opposite side, that this triangle is an isosceles triangle. So we've drawn our A, B, C here for our isosceles triangle. And what we're going to have here is essentially we're going to have our point X, right? So our perpendicular bisector. So this is perpendicular and it bisects our thing. So we know that this is also the altitude of the triangle. So it's like the proper length of the triangle. So it's exactly in half and it splits the triangle into 2 equal sections, right? So we also know that these angles would also be the same because this is the altitude of the triangle. So it's the perpendicular bisector of the triangle, so it bisects the angle. And then also another part about it being the altitude of the triangle would mean that it's perpendicular in the first place, right? So I guess the altitude part and the perpendicular bisector part is kind of mean the perpendicular part is kind of the same thing, but in terms of it bisecting, this means that this side and this side is the same. So what that we can gather from that is that AX will equal to XC, or equal to negative CX, and we also know that BX times AX will equal to 0. So that's kind of the 2 conclusions we can get from that. So we need to use that to prove that this side here is going to be an isosceles. Well, these 2 sides here are essentially going to be the same. So we want to prove these 2 sides are the same. So our goal is to prove that AB will equal to CB. Okay, cool. So in order to get to AB, what we can do is we can try to find what BX is plus AX, right? And what we can do from there is that if our BX plus our AX is, so that's what's going to be exactly our kind of thing there. And we know that our AX is just going to be our half AC. So we're going to get BX plus a half AC, right? And then what we want to find out what our BC is. So our BC is going to be BX plus our XC, right? So what we could get from here is that because it's BX plus XC, once again, it's going to be BX plus a half AC because it's the bisecting of that point, right? So once we can get that, we can kind of see that, therefore, we'll get that AB is equivalent to BC. So therefore, they're going to be that this is isosceles triangle. Isosceles triangle. Right? Alternatively, another way you can do this as well, so rather than going this way and this way, you can also talk about the angles within there as well. So you can also, like, if you did need to prove this in the context of vectors, another option to talk about proving this and doing this is essentially it's pretty relatively also straightforward in terms of what you do, right? All you need to do here is essentially say that you have angle BXA is equal to angle BXC, right? And you know that because of that fact, you also know that angle this equals to 90 degrees, and you also know that angle ABX equals to angle XBC, right? So those 2 angles, essentially that and that angle equal. So therefore, you know another thing is that 180 will equal to angle BXA plus angle ABX, so those 2 angles, plus, let's say, angle A, right? And that also means that this is equivalent to 180 is also equivalent to angle BXC plus angle XBC plus angle A. And those two are equivalent, right? So if you convert that to this angle, angle C. So if you equate that to the different things and you go 1 minus 2, what you'll get is angle A minus angle C will equal to 0. So you'll get angle A will equal to angle C. So that's another way to prove it if you didn't want to use vectors to do this proof.